Okay, so for the next talk, we have Arijit Kundu from IIT Kanpur, and he's going to tell us about Skyrme stripes in twisted double bilayer graphene.
I start by thanking the organizers for this nice event, as well as inviting me to present. So this is a work on this twisted systems. I think this is more towards condensed matter, less towards information, but there can be connections. This work is done with collaborators Harv Fertig from Indiana Bloomington and Dibokanthy Mukherjee, who was a postdoc with Harv at that time. But most of the heavy lifting was done by Devasmita, who is presently a postdoc at Regensburg. So I'll be talking about twisted bilayer graphene systems. I'll be talking about double bilayer graphene, but let me introduce bilayer graphene. I'm giving like 2-3 slides so that those who are not familiar can get a taste why we are excited about these systems. So these are two graphene layers which are stacked on top of each other with a relative twist angle between them, and the twist angle is typically tiny, of the order of a degree or so. And at that small angle, these two stacked together, these two layers, forms a kind of lattice, which we call Moire lattice, where the lattice spacing is can be hundreds of original lattice spacing. So this distance can be of the order of tens of nanometer, whereas for a single graphene, it's of the order of angstrom. So in this system now, most of the low energy physics is better understood in terms of interlayer tunneling. And you can kind of get an idea by looking at the stacked layers that there are regions which are like these situations where we have what you call AA stacked, where individual carbon atoms are on top of each other. Then the carbon atoms can be stacked, half of them. That's what one of them will call AB stacked, one of them will call BA stacked. So tunneling takes place, these regions, and this understanding the tunneling give rise to understanding of the system at the low energy regime. We can look at it in a slightly more deeper way. So these two stacked layers, you can think of, I have two Brillouin zones in the momentum space, which are now slightly twisted. And the small twist of the Brillouin zone give rise to an effective Brillouin zone, which is a Brillouin zone of this Moire lattice, which is much smaller. And all the physics we'll be talking about will happen around here. So low energy physics will take place around here. These are near the original K and K prime values of the graphene. Okay, so if we forget about the interlayer tunneling, one can think of these two K and K prime of the, these are both coming from the let's say one of the values of the graphene, and these are the two Dirac nodes. In presence of interlayer tunneling, these Dirac nodes will open a gap at a slightly larger energy away from the Dirac nodes. And you can see there are now computations of two energy scales. One is this distance and one is interlayer tunneling. And this computation of these two can make these bands pretty flat. Okay, this is one of the reason we are excited about this, to have a flat band. And why flat band is exciting? You know, that the interaction energy will play a much important role compared to kinetic energy. Further, these bands, of course, this is a very simplistic picture. In reality, what happens, there are multiple band foldings take place, and you can go through many different transitions. And these transitions are topological transitions because you're not really breaking down any continuous symmetries. So each time such transition take place, you generate Chern numbers of these bands. Okay, but the total time reversal is invariant. So any Chern number you generate has to be compensated by a Chern number, opposite Chern number of some other band. Typically, they are done by K value, I have a Chern number C, and K prime value, I'll have a Chern number minus C, and overall Chern number will be 0. But individual bands can have Chern number. Okay, this is broadly what is called fragile topology. You can generate bands with non-trivial topology fairly tunable manner because you have multiple tuning parameter. For twisted bilayer graphene, it can be twist angle, for example. All right, so three things: large lattice spacing, nearly flat band, possibility of Chern number. All three are interesting ingredients for novel physics. A large lattice spacing can give rise to, let's say, quantum Hall regime at a lower magnetic field, because you need a lower amount of magnetic field to push through enough fluxes. Okay, flat band is of course interesting. Symmetry breaking, topology and interaction plays a role here because of Chern number. Very exciting. All right, so what is twisted double bilayer? This is now a twist between two bilayer graphene. So graphene's the most stable structure is what is called is AB stacked, and this is a twist between two AB stacked bilayer graphene. All of the things that are exciting in the twisted bilayer graphene translates here. On top of that, now this band structure can be further tuned by an applied electric field out of it. So it is a further tunability of the problem. And this electric field also can give rise to change of Chern number, which are also consequences of fragile topology of the system. It's one of the kind of band structure, low energy band structure. And if you are familiar with graphene, you'll find this band structure fairly strange. They look, very strange looking because there's no particle symmetry to start with. And this is for a case of a particular electric field, and this is a different electric field, which is represented by some potentials on layers. And as you see, going from 5 MeV to 15 MeV, these bands go through topological transitions and have changed their Chern number. Okay, all right. So, as I said, I mean, some of the cases, some of the interesting physics can be understood even without going in the flat band limit, which is typically what we are typically excited about in the system. Even in the non-flat band limit, for example, this is a work with some experimental collaboration last year where we observed kind of cascade of Chern numbers in the Hofstadter regime of the system. Very non-trivial to observe in any other non-twisted systems. All right, but this talk will be on the flat bands of TDBG. So TDBG is acronym of twisted double bilayer graphene. This is long name, we often prefer an acronym. And these are nearly flat bands. Okay, so this one is a AB stacked graphene. So both the bilayers are AB stacked, AB stacked. This one is a AB and BA stacked bilayer graphene. So you see, these flat bands are flat band, nearly flat bands, but they're not as flat, as nearly flat as typical bilayer graphene. So typically, TDBG will give rise to nearly flat bands, but little bit of dispersion will be there. All right, so this is the kind of system we'll focus on. And of course, as you are nearly flat band, you can think of putting Coulomb interaction. And if you have the band half filled, you will expect some exchange interaction and open up gaps. In this case, I have opened up a gap between up and down spin, real spins. But this symmetry breaking can be different kinds. It can be valley pseudo-spin symmetry breaking. I mean, this is a prediction from the Sharma's group with some Hartree-Fock calculation, which allows to break spin polarization. You can allow to break superconducting, symmetry, and you will have superconductivity and so on. It's a Hartree-Fock. So you start by assuming you have some order, and you try to figure out whether that order survives and what is the lower energy ground state. So many experiments now. So this is one from 2020. This is a kind of interesting plot, but a little intimidating to look at first. So I have this top gate and bottom gate, which is on this twisted double bilayer graphene. And this is the charge neutrality. This is the point where is gapped. This gap is because of the electric field we have applied. This Ns by 2 is a place where you have exactly half filled one of the bands. So, and you can imagine, you can immediately see there is a gap, which is, this is just RxX plot, is resistivity, and Ns by 2, there is a gap. And this gap is so this is kind of a thermal activation, if you wish, kind of plot, showing that this gap has some it goes away beyond some temperature. Now, this is slightly different angle, and this gap is much less pronounced here. But if you apply an in-plane magnetic field, so in-plane magnetic field is typically Zeeman effect, right? So it kind of couples to the spin of the electron. The in-plane magnetic field enhances the gap. So this is a plot where increasing magnetic field gives rise to larger gap. So this tells us that the system is spin polarized, behaves like a spin polarized ferromagnet. It has been consistently reported in recent times. In principle, one can also go from a spin polarized state to a valley polarized state, but turns out that's not at ns/2, that's on 3ns/2. Some kind of interesting gaps open up at 3/4 filling in some of the samples. A lot of the physics here depends on sample to sample, because this twist angle and a lot of the parameters can vary minutely, giving rise to slightly different physics. This is another very recent evidence of another phase, which is happening very close to this half filling. You see 0.47 ns. This is half filling of the valence band, not the conduction band. Let me go back to this one so that the understanding is clear. This is what he called the first conduction band, and the black one is a K prime valley, red one is a K valley. That symmetry is also broken because of, in this system, the symmetries are broken because of relaxation. All right, so for the valence band, which is nearly half polarized, half filled, this experiment reports very unusual striped charge ordering in the system. Okay, this remains to be unexplained to some extent why there is this charge ordering. Yeah.
How do they detect it?
I think it's STM. All right, so this is the question we will be asking in this talk, that what happens if it dopes away from the half filling? See, half filling, we have a ferromagnet, look like spin polarized ferromagnet. And our answer would be Skyrme crystal. We will talk about what is skyrmion to start with. So skyrmion is a swirling spin texture in 2 dimensions in the real space. So it's a spin texture of something where it changes the direction of the spin from, let's say, origin to the boundary. And it does that in a very slow manner, such that the in-plane spins kind of moves around it. This is named after Tormi Skyrme, and he, I think, was working in nuclear physics. A lot of interesting relation to what you do nowadays, like excitations are vortex-like and so on and so forth. This skyrmion cannot be smoothly deformed into a magnetic ground state. And that is because they have a topological invariant. So this, what you call a pentriagon index, is something like maps how the skyrmion behaves in the real space to the block sphere of skyrmion. Okay, and this is an integer. As you know, integer cannot be smoothly deformed into another integer. So smooth deformation of the spins or the spin texture is not going to change this pentriagon index. It's a global property and is a topological invariant. All right. Now let's bring up quantum Hall analogy. Turns out this kind of skyrmions are the lowest energy excitations of integer quantum Hall state. Okay, and this is predicted, experimentally observed, and so on. So nu equals to 1 quantum Hall, as you all know, it would be filled one band, but you remember you have 2 spins. If you fill with half of the band, there will give rise to. So this gap between the 2 upspin and downspin bands are not going to be just Zeeman gap. That's tiny. So this gap is because of Coulomb interaction. Okay, so this exchange interaction is multiple times larger than Zeeman gap. So they form quantum Hall magnet. And an excitation can be adding an extra electron. But you see, now we have to add an electron of the opposite spin. And just adding an electron of opposite spin is going to be costly. Okay, so you have to somehow distribute the opposite spin in a smooth manner. And that's what gives rise to skyrmions. Okay, and this can be for electron and for hole. All right, so what happens in quantum Hall-like systems is that at a Skyrmian vortex, where the spin is kind of the vortex of the Skyrmion, is like a flux of magnetic field. I mean, this is coming from the Berry phase of the spin, spin which is kind of swirling around it. So this binds a charge of exact amount of Chern number. This is like you're bringing a charge from infinity to that point. It will bind a magnetic flux. So typically, for systems with Chern number, the extra charge density will look like exactly the integrand of the Pentarygin index, which is the spin density. So they will look similar. And that's why for states beyond half filling, such kind of spin textured state can be indeed of lower energy than just putting a charge with spin. All right, so this, in fact, one can move a little, make it more generic that if we indeed dope the system, then in the thermodynamic limit, the system forms Skyrme lattice. Okay, the Skyrmions will form. The Skyrmions are interacting because they have Coulomb interaction among themselves. They're charged object. This will give rise to a lattice of Skyrmion, which is typically called a Skyrme lattice. So evidence of Skyrme lattice would be that this would reduce the spin polarization of the whole system significantly. Okay, it not only makes one spin down, it makes all the nearby spins nearly flat. So this can be observed by experiment, just NMR study of quantum Hall systems, where it is a famous work by Badett in 1995, showing that as you move away even slightly from the quantum Hall, integer quantum Hall regime, the polarization of system drops rapidly. All right. Now, of course, in this kind of system, TBG or PDBG, we have nearly flat bands. One expects similar physics to play out. Turns out, in twisted bilayer, looks like the nearby low energy state would be a pseudo spin Skyrmion state and not a real spin Skyrmion state. There are experiments, but remains to be fully kind of convince everyone. That I think is still to be done. All right. This is another experiment where this is quantum Hall regime in the graphene. It's not a Hall in the spin sense. It's actually a CDW state. This is the same phase diagram Udit was showing yesterday. So this is a beautiful work. They look at this STS study. Look at valley texture, if you wish, locally, and one finds this is something called Meron anti-Meron pairs, like a Skyrmion. Okay, it's a topological defect of a state, which is like a quantum Hall state. So what happens in TDBG? What we find is that indeed the low energy state it has a Skyrme lattice, but it has some additional statements. One is that we find additional charge we put. If the charge is small, it mostly get accumulated one of the valley. The other valley remains, half filled and spin polarized. We also find that this system breaks a C3 symmetry by charge ordering. It forms a striped order in charge. We'll explain to some more details of it. Let me again focus you to these states. So we are looking at this conduction bands, half-filled conduction band, and this is the Berry curvature, how it looks like in the momentum space. You can see that this Berry curvature is spread out. It's not localized at a given point. It's just like quantum Hall. Quantum Hall would be a flat Berry curvature. In this case, it's flattish, not quite as flat, but still has a kind of spread out Berry curvature. And this is important for Skyrmions. Okay, I'm running little tight in time, but let me show you this. So this is, so one can think of this even at a non-interacting picture, how exactly, adding a Skyrmionic texture can give you more stable ground state at a filling which is higher than integer filling. How would I do that? So let's say I have some twisted double bilayer graphene conduction band, non-interacting, and I'm just going to put some spin texture on it by hand. So this is something you can think of. If I really form a spin polarization, then this would be the effective kind of magnetic field which is acting on it. So if I put a spin polarization which is sigma z, you see there is no texture in it. It's a uniformly polarized, but I'm breaking the lattice symmetry by introducing some smaller vectors. So I'm creating a lattice, but not really giving it spin texture. Okay? It's an artificial thing. These numbers really have no serious meaning in it. Immediately what you'll have is that this conduction band will break into two bands of exactly a half electrons on the each side. Okay. So this it tells us that if the band is half filled, you're most likely going to be forming a spin polarized band. On the other hand, if I introduce such a texture which has a real texture in the real, in a real space. So this is very similar to there, but now I'll have some sigma x, sigma y. I'm not showing it here, but this is the texture looks like in real space, and I'm projecting this whole conduction band into this texture. Immediately what happens is that the gaps open are not at n1 plus n2 half of the band, but at half of the band plus c number of electrons. It's a beautiful picture from the non-interacting picture that adding a spin texture allows, hints that there would be a stable gap at half filling plus Chern number. All right, this is about Berry curvature. This is something one has to keep in mind. Skyrmions are supported at situations where the Berry curvature is spread out. So if a Berry curvature is highly localized, the skyrmions are not going to be well supported. This is one example, again from non-interacting picture, that I have, evolution of the state as I change my electric potential. I'm going through a phase transition around 9.8, and I'm going from a kind of spread out Berry curvature to more localized Berry curvature. And you see this, as I go through that, there is a change of density of state which is passing through the gap. So kind of, in the state without Chern number, of course, I'll have the gap at the middle. State with the Chern number, I'll have the gap at middle plus C. So there has to be a spectral weight transfer. But we see that when the system do have a Chern number, but the Berry curvature is not very spread out, there can be states in the gap. So it may not be very stable. Okay, it's a very non-interacting naive picture gives you the idea that you need a spread out Berry curvature, band with Chern number to get a skyrmionic state to be stable. Of course, one has to look at whether this is the lowest energy state or not, and that's not trivial. Okay, so we are doing some Hartree-Fock. I'm not going to details of it. Let me just mention that we find always that when the band is, when the system is partial valley polarized, what I mean is that one of the valley is fully spin polarized, the other valley has all the excess charge, and that excess charge can have whatever texture and distribution. So that has lower energy than having a valley coherent state where charges are equally distributed. So this is one of the result we have. So this has one extra electron per unit cell. So this unit cell is now a much larger unit cell than Moire. So Moire is itself like 10 some nanometer. This would be one more order higher. So this is like, some 20, 30 of Moire unit cell scale. So this is what the Skyrme lattice is. Again, to remind you, so this is, we have added a small amount of electron, a dilute kind of density of electron on top of the half filling. So this electron gets captured by various Skyrmion vortices. And these Skyrmion vortices interact with each other through Coulomb interaction, forms a lattice. That's a Skyrme lattice. So each of the, so this is the picture where this blue kind of hill-like areas are the excess charge distribution. The color of the underlying spin texture is the z direction of the spin. These in-plane arrows are how the spins are rotating in plane. Okay, and this forms a triangular lattice, which has a lower Madelung constant and so on and so forth. So this makes sense. Now, the only issue is that as the spin moves from one vortex to next, is a little hard to see, but one vortex is going, all the vortex have a similar kind of swirling direction. So the spins has to go through a moving in the x direction to minus x direction as you go from one vortex to another vortex. So spins has to twist itself significantly. It's not a very favorable situation because this will act against the spin stiffness of the system. And this is also kind of a quantum Hall analogy. We know that this typically leads to a slightly higher energy state. So this can be resolved by having two vortices per unit cell. So in other words, if I have one more vortex here, which will have a swirling in the other direction, then the spins could go from relatively smoothly from one vortex to another, which is mentioned here. And if I do that, this is the texture I get. Now, immediately I see a couple of interesting things. One is that, of course, these spins now do not have to completely rotate. They can one vortex to another vortex, but this vortex now have opposite direction of swirling. So essentially, one single Skyrme lattice unit cell will have now two vortices, and each will bind one C number of charge. Additionally, now it's evident that this charge is actually forming a stripe-like order. This is simply a stripe order of charge. The spins also look like stripe order, but interestingly, the spiral orientation of the spin can be changed by overall spin orientation. That symmetry is not broken. If you start with a different SID, so let's say if you label all your Sx by Sy, Sy by Sz, Sz by Sx, the spin orientation will change. But the charge is not affected as expected. Now, interestingly, there is another ingredient in this. One of the value remains spin polarized. So even though from the numerics it looks like the spin orientation is independent of its axis, because the other valley is polarized, that is going to affect the spin polarization of this valley. So even though it looks like there is a spin orientation is independent of the axis, it is going to be determined by the spin polarization of the other valley. Okay. Not only that, even the charge order is actually emerges because of the exchange interaction between this polarized valley and this unpolarized valley. If we turn it off, this charge rotating goes away. It's a complex interaction which you do not understand fully how exactly the stripe order emerges out of it. All right, so let me just conclude. So many possibilities of this in experimental signatures. So the broken C3 symmetry immediately suggests anisotropic, spin transport, which can be observed in heat experiments and charge transport. System may form domains. So typically by allowing strains, you can break the C3 symmetry yourself and kind of nudge the system to form C3 symmetry in particular directions. The C3 symmetry, of course, suggests that the system will also go through another transition to a charge ordered state instead of, and this might be also observed in transport. The anisotropic spin stiffness can also be observed in spin wave studies at low enough temperature. So this work is under review. I thank you for your attention.
Questions?
So I was a little confused by your statement just a couple of transparencies ago, this one. So you said there's some band that's fully polarized.
Yes, one of the valley remains spin polarized.
Fine.
Yeah.
Let's say that direction, since there's no spin orbit coupling, just call that direction Z. Then there's locally some projection of the spin in the XY plane, right?
Yeah.
So there's still a U1 symmetry.
Yeah, the U1 symmetry will be there.
But it's broken.
Yeah.
Spontaneously broken by this texture.
So the Z direction will be fixed by the Z direction of the valley, other valley.
Yeah.
But as far as I understood, the U1 symmetry might still be unbroken, which will be broken by choice of state.
So this state breaks that.
Yes.
So there should be a ghost stone mode.
Yeah, there'll be ghost stone mode.
So you can see that by specific heat or thermal transport or
which will be very anisotropic.
Extra thermal transport.
Yeah. Absolutely.
More questions?
Yeah, I have. Arijit, nice talk. These flat bands which you have in graphene, you're saying that they are like quantum Hall. They have Chern numbers. Do they give rise to edge states? Have anybody seen? They should have edge states, right?
Yes, I mean they will, and there are experiments which shows it. But typically what happens in these systems, they have a lot of structural deformities. What happens is that this angle is typically not very smooth throughout your sample, at least until the kind of now, whatever people have prepared. So they have regions of this sample where they will have a uniform angle, then nearby regions with different angles, and there will be domain walls which will flow inside.
I see. But
So this has been observed.
okay, so if these fermions form, they will push out the charge to the edge, right? That's what should happen. Right?
No, so this is no, this is a bulk physics. You are adding an extra charge. So that extra charge you are adding by hand. It's not taking a charge from the edge or pushing the charge to the edge.
But if I have the ground state of a quantum Hall system, and if I have one fermion,
Yes,
then
that
does
would be
it
an
have no-
excitation on your ground state.
Yeah, but does it have no implication on the edge as far as its charge is concerned? It should have, no?
I don't think it has a. I may
Charge
be
or
wrong.
spin,
I
right?
don't think it has a direct implication to the edge. I don't know, Ganpathy. Yeah.
Yeah, so it's like doping the bulk. You dope the bulk, but the charge collection. Everything is all bulk.
Yeah, it's a bulk physics.
But if it is a finite system, the charge doesn't go and accumulate on the boundary? Why?
Because
Anyway,
it forms.
Okay, fine.
So you see, okay, if you add one extra charge, it will form a Skyrme lattice, a single skyrmion. Okay, but if you think of a thermodynamic system, adding a finite number of electrons, they will start forming these skyrmion lattices. A lot of skyrmions will be there. They'll interact to form a lattice. So this is a incompressible state, which may not be true all the cases, all the times though.
Yeah, that's why I expect if it is incompressible, I expect things to be pushed to the boundary where it's compressible. So that's the.
Okay, at least I do not know.
Okay, fine. Okay, we can talk about it later. Thank you.
More questions? Okay, I actually have a question. So these are spin textures, but of the order of even like few Moire scale. They should be seen in the few structures like something like SQUID, right? They should be able to see this.
Absolutely. And not only that, there are a lot of interesting ways one can see this. I showed the STS studies, but apart from that also, this local magnetic field can give rise to local Landau levels. That also one can probe. But these are all local measurements. I think local measurements are difficult. When I think of transport, then spin wave and that's all.
This can have spin wave from many origin.
Absolutely.
This is not the unique origin.
So local measurement would be a perfect way to look for this.
And the second question is that even though you are doping away very little bit from the half filling that you do.
Right.
So this order is still a very small fluctuation on top of whatever the background you had, because we already have same polarization on two, and there is
it's interesting because the spins completely reorganize themselves. The ground state spins, which was purely spin polarized, reorganize itself, and the polarization drops away by so the effective G coupling, G effective, becomes like of the order of 100 or something like that. So it significantly drops the polarization. So spins reorganize themselves, at least from quantum Hall cases. Okay. So it's a small fluctuation, but the ground state reorganizes.
More questions? Yeah.
Yeah, Arijit, can you explain once again the role of interaction in forming this Skyrmian lattice?
It allows to break symmetry. That's typically starting point, right? A Coulomb interaction has a larger symmetry class, and you allow it to break the symmetry, form a lattice. All of these are done by interactions. So any symmetry breaking you think of, instead of including Skyrme lattice formation.
So this interaction, do you need only interplanar or intraplanar in your analysis?
Yeah, all of it.
So you have taken
yeah.
Coulomb interaction between the layer.
It's a screened Coulomb interaction because you have gates. So you have to take into account how gates are screening it, but then you take into account inter and inter. It's a Coulomb interaction.
And another question is that, for example, when I'm doping away from the half filling, and suppose the interaction strength is not weak, it is very strong. I mean,
Sorry.
if the interaction strength is strong, I mean, real, if I do not Hartree-Fock, if I want to do a real many-body analysis.
I don't know what is real many-body.
Yeah, Hartree-Fock is a
Okay.
weak coupling theory.
Okay, so you further including, okay.
Yeah, then how much of this physics will remain?
Again, I mean, experiments can only tell. I mean, this, Hartree-Fock.
Yeah,
You're
we
asking
know,
the
right?
question why Hartree-Fock works. I
Real
think-
many-body is DMFT or quantum Monte Carlo. Yeah.
I mean, there are a lot of reasons one can give why Hartree-Fock works. Typically, the most textbookish answer would be presence of a Fermi surface, but very hard to say. Of course, the orders of magnitude. For example, let's say we compute a TC or something will be off in Hartree-Fock. That's yeah. But Hartree-Fock is a thing you can do, right? Beyond this is.
Question? Sumathi had a question? Okay. So if
Just
not,
one-
first let's thank
Ankur,
Arijit.